Hi boys and girls, hi Vasha and Vidya. In the last classes we have completed the last module that was mostly on topics from wireless communication. So their videos were not really necessary. You saw some derivations, some mathematical operations, some explanations, and most of this you can learn with the text and the presentations I shared with you. Now we are going back to a topic in the third module. That is a very important topic, that is the intersymbol interference. So I told you in baseband transmission, that is without any digital modulation, you will be transmitting your bits over a channel, and in the channel you encounter two effects. One is your good old enemy, the additive white cosine noise, and the other is the intersymbol interference. So today's video is about the intersymbol interference. So let me start with that presentation. So what you will learn in this section is that first you will understand the mathematical model of intersymbol interference, and then you will learn the effect of ISI on baseband transmission. Then you will learn and prove the Nyquist condition for zero ISI. So what is the condition of the channel spectrum as far as this ISI is concerned? What should be the condition for zero ISI? Then you will learn about certain pulses that can minimize ISI, certain pulse shape that can minimize ISI. You will come across the raised cosine spectrum, and then you will understand the receiver design based on root raised cosine pulses. So you understand quite a bit of things in this video, and I will supply some simulations to augment your understanding. Now when you look at the signal design for band limited channels, baseband transmission of the sequence IN, so suppose you want to transmit bits or maybe digital signals, no practical systems can easily, practical channel can respond to these signals. So what you do is you embed or you superimpose it on a pulse shape GT. This pulse shape, intuitively the rectangular pulse comes to your mind, but rectangular signal is a very impractical signal. Sometimes you use a Gaussian shape, sometimes you use rectangular. Anyway, some sort of pulse shape is used. Usually that amplitude of the pulse shape will be equal to individual values of my sequence IN. So the transmitted signal looks like some Vt that is equal to some sigma n equal to 0 to infinity In gt minus nt. So this gt is modulated in magnitude by the value of the sequence In. So it should be noted that gt is band limited such that its spectrum is outside the band f greater than w. For gf is 0 means the spectrum of this signal is outside is 0 outside a certain band w. And now this gt that is given to the channel, this channel may have some impulse response. We assume that it is a linear, the channel is also a linear time invariant system with impulse response as ct. So that this bt, this vt is when it vt passes through the channel, what happens is that gt gets convolved with my ct. So the total together with my pulse shape as well as the channel that has a total impulse response of bt is gt convolution ct. This will be very clear from the next diagram. So if you come here, this is a baseband transmission system. Here you see these digital values or maybe binary values coming into this thing. This is pass through a system whose impulse response is gt. This is actually my transmitter pulse shape, or this is my transmitter filter. Okay, so this in is passed through the transmitter filter to generate your signal Vt. Okay, and this Vt is passed through an additive white Gaussian noise channel whose impulse response is Ct, and this one upon passing through this channel, a noise, a Wg and Nt is added to my signal. So the received signal Rt is equal to, so this Gt together with the Ct that we can consider as a single linear time invariant system whose impulse response is Bt, that is equal to Gt convolution CT. You know how LTA systems do commute and how you cascade LTI systems. Probably you learned in your signal science system course. So this I call it GT together with the CT. I call it as I say BT, so that output of this channel, output of the channel RT is equal to n from 0 to infinity in BT minus NT. This BT is GT convolution CT. Plus I have this noise entering in the channel, that is say NT. So this is the received signal coming here into my receiver filter. So at the receiver also I have to have a filter. Let me call it HT, so that output of this filter HT, this is my actual output of my receiver filter. So this GT is my transmitter filter, CT is my channel impulse response, and HT is my receiver filter. So this YT is nothing but sigma I xn t minus nt plus ET. What is this X? Because this whatever is coming here, this RT is convolved with GT. This RT is nothing but IN BT minus NT plus eta T. So this BAT is convolved with HT. What is BT is nothing but GT convolution CT. So together BT convolution CT convolution HT I mark as say X of T. So this becomes IN XT minus NT plus eta T. Eta T is nothing but this noise NT, the AWGN, it passes through the HT. So the noise component coming out of this I mark as eta T, which is nothing but NT convolution HT. This is NT convolution HT, and this X is nothing but it is together with the transmitter filter, together with the channel, together with my receiver filter. So this is the overall impulse response of the system, that is GT convolution CT convolution HT, that I mark as XT. Now if you closely look at this equation 4, you will understand the effect of the ISI. So this I can sample at every say at every t seconds, or every at a rate of 1 by t, so that I can take this as y or kt or yk simply. So this becomes n from 0 to infinity in x n minus k plus some eta k. Only thing is I sampled this equation, the signal in equation 4. So if you look into this equation, yk equal to I sigma n from 0 to infinity ik xn minus k plus eta k. So if I take the value for n equal to k, this will be ik times x0, ik times x0. This is for the case n equal to k, plus some other terms come here for n not equal to k, that is n not equal to k, ik xn minus k plus eta k. Now this x0 can be made an arbitrary scale factor. I can make it a 1, so that I have this equation yk equal to nothing prevents me, nothing stops me from doing that. I can make this x0 a 1, so that yk is equal to ik plus n not equal to k, ik xn minus k plus eta k. Now if you look into this equation 7, you can see that this is what I need for at n equal to k. This is the intended symbol. This is the original information bit or information symbol transmitted at n equal to k. This is what I want. Along with that, I get two unwanted components, and this is nothing but this term is due to a convolution between ik and other values of x, so that this term is called my intersymbol interference, or ISI. And this is my good old enemy. This is this is my AWGN. Okay, so I encounter my two enemies here, yk equal to ik. This is my desired thing. Then I have two undesired components here. One is ISI. This term is called the intersymbol interference, or ISI, plus eta k. This is my nothing but my additive white Gaussian noise. So this is how ISI and my AWGN affects my symbols. Okay, so if I say jokingly, this is like when you marry, you get your bride or your groom. This is a wanted bride or groom. So along with that, you get unwanted elements like your in-laws, like your father-in-law, mother-in-law, brother-in-law, etc. And this is your ISI, because this is coupled with your bride. Okay, but you want the bride only, you don't want your in-laws. But when you go for the bride, you get the in-laws also. Okay, and then I have my old independent other enemies are there. Anyway, I have other enemies. and that is my AWGN. So the first term is my desired signal, and this term, this is my ISI, and this is my good old additive white Gaussian noise. Now let us see. Now you don't want ISI, so there are two ways in which you can control or minimize ISI. One is you try to minimize ISI with proper pulse shapes, like you design your GT, HT, etc. in such a way that you minimize ISI. So it is like you want your bride alone and you don't want your in-laws. So the easiest way is to you find a bride or a groom without any father or mother or brother or other unwanted people. So that is one way. That is not an easy thing. So that is one way. Another method is that you try to neutralize the effects of ISI. That is, you marry a beautiful girl, and then your brother-in-law or your sister-in-law is causing you trouble. So what do you do sensibly? So what you can do is you have to coax her brother into a marriage. If he is unmarried, so you coax him into a marriage. So you find a bride for your wife's brother, so that what will happen when he marries, because his wife and his brother-in-law will be nagging him, so he has less time to trouble you. So what we do is, I have ISI, so what I do is I put another system that can counteract this ISI. So in this joke I say I have an unnecessary brother-in-law. What I do is I find a bride for him, so I put a new system that can neutralize the effects of the unwanted effects of ISI. So that is the concept of equalization. Equalizer is nothing but an LTI filter. You add one LTI filter called an equalizer, and that effect of the ISI will be minimized. Anyway, that is not included in your syllabus. So another thing that is included in your syllabus is the Nyquist theorem. This theorem, due to Nyquist, says that the necessary and sufficient condition for zero ISI, so that x nt, what is x? This is my GT convolution, CT convolution, HT. So this should be an impulse that is together the total system, total LTI system, GT convolution, CT convolution, HT should be a 1 for n equal to 0 and equal to 0. Otherwise, this should be an impulse function. So that when in is convolved with this x and t, what happens is only in comes out and no other term, no other ISI comes. It is very difficult to have such a thing. But if for this to happen, the Fourier transform of this xf, what is this? This is nothing but gf times cf times hf, because you know that xt is a convolution between the two. So if there is a convolution in the time domain, there should be a multiplication in the frequency domain. So x of f is nothing but gf. What is that? That is the spectrum of my transmitter filter times cf, that is the frequency response of my channel, that into the frequency response of my receiver filter. So xf is that. If the Fourier transform of xf satisfies this condition, that is, if I add up this periodically, this periodic sequence, if that comes to capital T, that is a symbol duration or inverse of my rate of sampling, then my channel will have zero ISI. So this should be carefully understood. This is another theorem, famous theorem by Nyquist. This states that the necessary and sufficient condition. So that means this is an if and only if statement. Okay. So for zero ISI, I have to have x and t equal to is a delta function. For that to happen, xf should satisfy this equation, m from minus infinity to infinity, xf plus mt equal to t. Okay. So this need be proved. It is proved as follows. It is a very simple proof. That is, xt is nothing but the inverse Fourier transform of xf, that is minus infinity to infinity, xf e raised to j2 pi ft df. I take samples of this x and t. This I know that it is a delta function for zero ISI. So x and t equal to minus infinity to infinity, xf e raised to j2 pi n ft. Only thing is I replace this small t by n capital T. Now this integral is from minus infinity to infinity. What I do is I split this integral down to many integrals. So I take I take the duration from minus 1 by t to 2t to plus 1 by 2t. Okay, this is one interval. Okay, plus 1 by 2t to minus 1 by 2t. Generally I write 2m plus 1 by 2t, 2m integral 2m minus 1 by 2t to 2m plus 1 by 2t x of e raised to j 2 pi nft df. Then what I do is I sum up for all possible values of m from minus infinity to infinity, so that this summation of integral is nothing but my good old integral. What happens is m from minus infinity to infinity, I can take out this m, I can move this m to here, so that this becomes x f plus m by t e raised to j 2 pi nft, so that this limit is changed as minus 1 by 2t to plus 1 by 2t. Now I can interchange this integral with the summation, so that this integral I can push outside, and I can this is in m, so that m from minus infinity to infinity xf plus m by t e raised to j 2 pi nft. So this is what I want to work with. So this summation I call as a capital BF. BF is nothing but minus infinity to infinity xf plus m by t. If this BF, this value is equal to t, then my theorem is proved. That is my theorem. X of f plus mt, that should be t. Okay, xf plus m by t, that is equal to t. So that is my theorem. So now what I can see is this BF is this is a summation of xf. This is a periodic signal. This BF is a periodic signal with fundamental period capital 1 by t, 1 by capital T, because this is periodic with a fundamental period in frequency. I am talking about it's periodic in frequency with a fundamental period 1 by t. So that if something is periodic, I can write as expanded as a Fourier series. So I can write BF as n equal to minus infinity to plus infinity Bn e raised to j 2 pi nft. Okay. Now what is this Bn? This is nothing but my Fourier coefficient. I have the good old equation for my Fourier coefficient Ck or Bn here. This is nothing but 1 by period. 1 by period. What is 1 by period? 1 by 1 by t, it becomes a t. Over one period, what is one period? It is 1 by minus 1 by 2t to plus 1 by 2t. Bf e raised to complex conjugate of this e raised to minus j 2 pi nft df. So that this comes as a function of n. Now if I compare this equation 13 with equation 11 here, you can see that x and t is this bf e raised to j 2 pi nft, and bn is t times integral bf e raised to minus j 2 pi nft, which says that bn is nothing but t times x minus nt. All you have to do is make this x minus n, so that this becomes part of this bn or bn by t, so that bn is t times x minus nt. So Bn is and you know that x nt, we said it is a delta function. So when n equal to 0, this Bn should be t times xn. Xn is a delta function, so at n equal to 0 its value is a 1. So Bn equal to t for n equal to 0, and Bn equal to 0 for n not equal to 0. So by equation 12, this Bf, when Bn has only one value, that is I say that Bn is this is t for n equal to 0, everywhere else it is 0, so that this summation becomes Bf is nothing but t into e raised to 0. There is only one term in it, because Bn is 0 else everywhere except n equal to 0, so that Bf is nothing but my t, and that is my proof. Bf is nothing but sigma m from minus infinity to infinity xf plus m by t, that is equal to t. This is a proof of the Nyquist theorem of 0 ISI. This is very important. You do with paper and pencil and understand that. You may refer the book Digital Communication by Provocus for all this. And what is the meaning of this Nyquist theorem? You can see that this sigma xf plus m by t equal to t. So if let us consider a few cases here. You know that x of f is nothing but gf times ef times hf. So it is band limited in such a way that xf equal to 0 for f greater than say w. Now let us consider a case where this 1 by t is greater than 2w, so that this x of looks like this. That is, this 1 by t is greater than 2w. This is the width of my pulse x of f. This is the spectrum of my xf. So this is my sampling rate 1 by t. Somewhere here I have 1 by t. Yeah, here I have 1 by t. Okay. And if you look here, this is from minus w to w, and here this is my 1 by t. So this width is w, because from here to here it is w, from here to here it is w. So this is my next sampling interval, that is 1 by t. So this point is 1 by t minus w, and this is 1 by t plus w. And if you look here, this is, if I take these are replicas of the thing, they are added up. So this is minus 1 by t minus 1 by t plus w. Okay, this will be minus 1 by t minus w, etc. And if you see here, you can see that this value may be t, but here it goes down. It is not t. And this is sigma xf plus m by t. This is xf. Okay, this is xf, and this is total thing is sigma xf plus m by t. So that you can see that here it is 0. So the condition is not satisfied here, because here throughout this value, this is not a flat t. Instead it is here it can be, it becomes a 0. So this is a case with the ISI. Now let us another case where these they meet exactly, that is 1 by t is 2w. If you here this is my 1 by t, this is w, this is w, so that 2w is 1 by t. This is 1 by t plus w at this point, and this is my minus w, this is minus 1 by t, this is my minus 2w, okay, which is nothing but minus 2 by t. So if you here, if you overlap and add, if you add up this way, again you can see that it is this sum is not t always, because here it may be t flat, then it comes down here. So here also I have ISI. Here also in this channel model also I have ISI. Now, if they overlap a little, you can have 0 ISI. So that is depicted in the next figure. That is when 1 by t, that is this rate should be less than, or my rate of sampling should be less than 2w. Then only I can say there is 0 ISI. So that case is depicted here. If you here, it is w, this is 1 by t. So that there will be some overlap, because this point is 1 by t minus w, and this is my w. Okay, so that these points overlap here. So if you add them up, it is always a capital T. Here it is a T. Here it reduces, but that is compensated by this component. So when these things are added, so you get a T throughout. So this function is nothing but capital T. This is the case with the 0 ISI. So this is how you understand the Nyquist theorem for 0 ISI. Now let us go to another interesting topic. I told you by signal design you can, by designing properly this GT and HT, signal design means design of GT and HT. I don't have much control over the channel. I assume that it is flat. I have no other option. So I have control over my GT and HT. So by properly designing that, I can have limited ISI. So one such function that can minimize ISI is called the raised cosine function, or raised cosine pulse. So let us assume that the spectrum of the channel is CF equal to 1. I don't know about my channel. This is out of my control. So I assume that this is very friendly. That is CF is 1 throughout. That is within this operating range frequency, F less than W. This is a 1, so that XF is GF times CF times HF becomes simply XF equal to GF times HF. Now the raised cosine spectrum of XF, if you are taking XF as a raised cosine spectrum in the frequency domain, the spectrum looks like this. XF is T for F mod F less than 1 minus beta by 2T, and this is T by 2 into 1 plus cos pi T by beta into mod F minus 1 minus beta by 2T in the range of 1 minus beta by 2T to 1 plus beta by 2T. Outside 1 plus beta by 2T, this is a 0. Okay. You will have to understand this. Okay, the spectrum looks as in figure 5. I'll show you some simulations on this. Rather than actually showing you this, I will show you some simulations. Let me go to that code. I have written some Python codes for that. This plot affects yeah, this beta is called the roll-off rate. This thing, this beta is roll-off of this spectrum, roll-off of this cosine pulse. Now let us assume that this t is 5, okay, and I take, so I am interested in the frequencies from minus 1 by 2t to plus 1 by 2t. So I take it from say t raised to minus 1 to minus 1 by t to, I'm interested in all frequencies from minus 1 by t to plus 1 by t. So this is this I have selected a frequency range from minus 1 by t to plus 1 by t plus with an interval of 0.001, and I have chosen some beta value. So I have to understand the behavior of my roll off for different beta values, say 0 0.2, 0.5, 0.8. I have some small issues with when I use a 1 exactly. So I can rewrite the program, but I chose a easy exit this way. It's almost 1.99999. It's almost 1. Okay, so for different beta values, for these different beta values, I have to compute the spectrum and plot and appreciate them for different beta values. So this is how I yeah, these three statements, if, elif, and the last elif, that realizes these three conditions. Okay, these three conditions. So that is I call it as a capital H. That is my HF, whatever XF, that H vector. So I plot it against different frequencies, and I label for different. I give the legend for different beta values. So the REPR is the actual value of beta. This R prime is for inserting the latex symbols, and I give a legend and I do this. So now you might want me to run this code. I will run this code. This name is plot SXF. Okay. I will improve it a bit, enlarge it a bit. I will write plot run plot xf it is plots xf dot py. Now you can see that you see this window. I will enlarge this window. You can see that for different values of beta, that this is how your xf or your overall frequency response, that is overall frequency response means gf times hf, that behaves. Now this blue curve, that is for beta equal to 0. You can see here these legends, you can understand beta equal to 0. You can see that this is my 1 by t, which is nothing. I assume that t is 5, so that this is my minus 1 by t, 1 by minus 1 by 5, or minus 0.2. You can see that it comes here, and this is nothing but this point is my minus 1 by t, minus 1 by 2t, I'm sorry, minus 1 by 2t, so that it becomes minus 1 by 10. It is minus 0.1. You can see that, and here this point is my 1 by 2t plus 1 by 2t, that is 1 by 10, that is 0.1, and this point is 1 by 2t, 1 by t, I'm sorry, this point is plus 1 by t, that is 1 by 5, that is 0.2. And you can see that outside this minus 1 by t to minus 1 by 2t to plus 1 by 2t, it is 0 for the case with the beta equal to 0. Okay, for that roll off, 0 roll off, you can see that it's almost a rectangular pattern coming here. Now as this beta increases, say beta equal to 0.2, that is an that is a red curve here. You can see that you can see the roll of changing, and it passes through exactly through the middle, that is 2.5, and this top value must be 5, that is t. Okay, this is t, which is 5. I assumed it to be 5. So at 2.5, all these curves should be going through this point. All these curves should be intersecting at this point. So this is the value for beta equal to 0.2, and this is the value for beta equal to zero point 0.8, zero point 0.5, and this for beta equal to zero point 0.8. This red curve is for beta equal to zero point 0.8, and this violet curve is for the beta equal to 1. This is almost 1.999, etc. It is almost 1. So this is how my spectrum or my raised cosine spectrum behaves this way. Okay, I hope you understood this. You try to run this code. You try to run this code and appreciate that. You try to run this code and appreciate that. Now let me go back to that presentation, and again I will enlarge the presentation. So this is how the root raised cosine pulse, so plots of xf for different beta values, they look like this. And now what you can do is this is a spectrum xf value. So correspondingly there is a value for x of t, which is nothing but the Fourier inverse Fourier transform of this equation. What is this x of t? That is nothing but gt convolution ht, because ct I assume that is a 1 flat, because ct is cf is 1 throughout our interstellar frequency range, so that ct is a delta function. So xt is nothing but gt convolution ht. So that thing xt comes as, if you take the inverse of that one, you don't have to know the mathematics of that. This is sin t by t into this is sine 2 pi t by 2 pi t. This is sin function sin t by t into cos pi beta t by t divided by 1 minus 2 beta t by t whole square. So this that variation of xt is shown in this figure. I will show you a simulation of that. I will run. So here I have the code for that. Yeah, these plots are here. So what I do is I import these things, and this is actually not needed. It's part of some other code. So you can see that I select a time from say t is from say minus 40 to 40 with an interval of say 0.1 or an increment of 0.1, and t as in the previous case I selected it as 5, and these beta values I selected as 0, 0.2, 0.5, 0.8 and 1. So for these different beta values I compute this function. Okay, only thing is I put as 3 different entities and multiplied and divided for the ease of computation, nothing more. Now when I plot this, I get my xt. So I will run this, run plots. Now you can see that this is how the signal xt looks like, the pulse xt looks like. When beta equal to 0, you can see that there is a blue curve. This blue curve is for beta equal to 0. That is, this is almost like your sinc function, because when you go by here, when beta equal to 0, this is a cos beta, cos 0, that's a 1 divided by this beta becomes a 1 minus 0. So it's a 1 by 1 into sinc t by t, which is nothing but a sinc function. So when beta equal to 0, it looks almost like a sinc function. Earlier you saw that it was a x of f is a rectangular one, so naturally this should be a sinc function. There is nothing fanciful about that. And when you increase this beta to 0.2 etc., you can see that these side lobes levels becomes very small. The side lobe levels becomes very small. So this is how xt, which is nothing but gt convolution ht, behaves for different values of the roll-off. So let me continue with this presentation. So this is how the pulse with a raised cosine spectrum. This is a raised cosine pulse. Now you must understand that if these GF and HF are equal, okay, one part is my transmitter filter and the other is a receiver filter. I assume that the channel is flat. Now if this is nothing, this XF is nothing but GF times HF. If GF and HF are equal, if they are identical or matched, then both GF and HF should be root of XF. Okay. So if you have to consider the square root of this function, square root of this function, That inverse, that will be equivalent to gt and ht. That will be gt equal to ht. That follows this equation. God save you if they ask for this equation. Usually we use it for designs and all. We design with computer programs, and I don't think anyone will ask you. Probably they will ask you about the shape of this one, etc. That you have to understand. So gt is equal to ht, that is equal to this. This is called a root raised cosine signal. So you can have a root raised cosine signal function in your as gt, that is transmitter filter, and a root raised cosine function, identical function in your receiver, so that this gt together with the ht will form a something called a raised cosine spectrum, and then you will have zero ISI. So this is how the such a root raised cosine function will look like this. I will show another simulation for that. Where yeah, this is a GT pulse. I call it a GT pulse. Okay. Here also it is an implementation of this equation for different beta values. You can see that here I have some three conditions for this. This is nothing but implementation of this equation. Okay. This is an implementation of this equation. Okay, this is another implementation of the equation, so I will run. You can appreciate this. These are four different values of beta. Your RRC filter looks like this. This is for beta equal to 1. This outside curve is for beta. This is for beta equal to 0.3, 0.5. For different values, you can appreciate the root raised cosine pulse. So what happens is at the transmitter I have a root raised cosine signal, and at the receiver I have another root raised cosine filter, so that I have zero ISI. So we come to the end of this presentation. So in this video you understood the mathematical model of ISI, then you understood the effect of ISI on baseband signals, then you understood and proved the Nyquist criterion for zero ISI. Then you learned about certain signal models with which you can counteract ISI, that is, you learned about the raised cosine spectrum and the corresponding pulse. Then you understood how to design a transmitter and receiver with the root raised cosine filters. And that is the end of this. Thank you all.